Hi everybody, we are on our AP Review Topic 7, Horizontal and Vertical Motion, and I thought I would begin by going over a few of these concepts. Now, we have horizontal and vertical motion, which we cover in Calc BC in the fall, and then we do parametric and vector motion along a curve in the springtime. And so this piece of notes is found on our Google Classroom under Unit 10 Notes, and you can look for it's the very first thing on there, I believe. It's called Comparing Motion Types. So on the 2020 AP exam, as you know, we are not going to have any kind of parametric and vector motion. Usually I focus on that. I focus very little on horizontal and vertical motion for the AP review. But this year, there is a good chance, I would think, that they will be asking you some questions about horizontal and vertical motion, since they're not going to be asking you any questions on parametric and vector motion. So let's go over this. We're going to spend a little time on this. Just a review. Position. If we have horizontal motion, we can let position be x of t. If we have vertical motion, we can let position be y of t. And we can always let it be s of t. Those are the common things. Of course, these we can let them be other variables as well, but usually t represents time, and x for horizontal, y for vertical, or just in general s. So velocity is the derivative of the position function, and acceleration is the derivative of velocity, which means acceleration is also the second derivative of the position function. Speed. Speed is always the absolute value of velocity. So to find the speed at a specific time, you find the velocity at that time and take the absolute value of it. When is speed increasing or decreasing? Well, when we ask if any function is increasing or decreasing, we look at the derivative of that function. We see if the derivative is positive or the derivative is negative. So we want to find the derivative of speed and see what time values make it positive and make it negative. All right, so the derivative of speed, which is the absolute value of velocity, when the derivative is positive, the speed is increasing, and when that derivative is negative, the speed is decreasing. If you have a calculator, this is very easy because we have all these functions on our calculator that make that very easy to see. Without a calculator, though, taking the derivative of an absolute value function, it can definitely be done, but it's a little tedious. So we use this result. Speed is increasing when the velocity and acceleration have the same sign, either both positive or both negative. Speed is decreasing when velocity and acceleration have different signs. And that's a nice outcome to use. All right, another couple of definitions. Displacement from time A to B is the position at your final position minus your initial position. So S of B minus S of A. The displacement can be a negative value if you end up to the left or below where you began. So yes, displacement can be negative. Total distance traveled is the integral of the speed function. It's integral of speed. Since speed is always positive, the integral of an always positive function will always be positive. So total distance traveled has to be positive. Okay. This integral is very easy to find if you have a calculator. Without a calculator, though, it gets very tedious again. So you need to add up all the distances going up or to the right, with all the distances going down or to the left, depending on if you're vertical or horizontal. So set v equal to 0, find the times the particle changes direction, and find each distance traveled, then add them up. All right, so horizontal and vertical motion, in a regular AP year, we cover this because these tend to show up in multiple choice questions. All right, so regardless of this year, we would always cover this material because you will see these on multiple choice questions. Okay, let's take a look at some examples. If you grab your notes packet or your worksheet packet, I'm going to begin with the 2016 test. This is from the AB test. We do not see FRQs on this topic, only on the BC test, because again, they cover motion along a curve instead on the FRQs. So I do want to go over this with you, particularly for our 2020 year, so that just in case you do see something on the FRQ test this year, you'll be familiar with it. All right, so here's the question. Well, here's the information for this question. For time greater than or equal to 0, a particle moves along the x-axis. The velocity is given by this function. This was number 2. It's with a calculator, so I'm going to grab my calculator. The particle is at position. It's at position x equals 2 when at time equals 4. So they're giving us x at time 4 is equal to 2. All right, part A. At time t equals 4, is the particle speeding up or slowing down? Speeding up or slowing down? Well, we can do this two ways. We can do it using the particle is speeding up when acceleration and velocity have the same sign, or different signs that will be slowing down. Or we can go ahead and take the derivative of the speed function at 4. Since we have a calculator, we can do that. So I think since we do have a calculator, I think I'm going to do it that way. The speed at time 4 is equal to the absolute value of the velocity. You know what? Speed, and let me just write speed. Speed is equal to the absolute value of velocity. All right, so the derivative of speed at time 4 is equal to the derivative of the absolute value of velocity at time 4, and we can let our calculator find that value for us. So let's go to our calculator, clear out what's in there. All right, I'm going to, since this is a long FRQ, I'm going to go to y equals, and I'm going to go ahead and put our velocity function in for y1. Remember, when we're doing any kind of motion problem, the velocity function, the derivatives are what are great to have stored in for y1, and if it's a particle motion, and for y2 as well, for the y coordinate. All right, t squared divided by 2. Okay, I do a quick double check, make sure that's right. Okay, so now I need the derivative of the absolute value of my y1. So math 8 of the absolute value. The quickest way I know of to get to absolute value is second F2. And it's right there, absolute value. It's the quickest way. It's also under the math function if you want to go there. And then for y1, the velocity is stored in my y1, so alpha F4 will give you your list of y1, y2, etc. And then we're going to, oh goodness, I just exited out of that. Let me quickly get it back. And there's that, and then we want to evaluate that at time 4. And we quickly find that the derivative of the speed is negative 1.164, which is less than 0. That means the speed is slowing down at time 4. So the particle is slowing down at time 4. Okay. Part B. Find all the times in the interval from 0 to 3 when the particle changes direction and justify your answer. Well, the particle changes direction when the velocity changes sign. So we want to find the times when the velocity changes sign. So, and we're only considering times from 0 to 3. So I will write v of t changes sign when t equals, okay, now we go let our calculator do the work. I have v stored in for y1, and I usually keep 0 stored in for one of the other y values. And now I'm only wanting to consider from 0 to 3. So 0 to 3. And I don't know what y values I need, but I know I need to include 0, because we want to see where the velocity changes signs. So I think I'll just leave it like that. As long as you're including 0, you should be in good shape. Ooh, I liked my y values there. That was pretty good. Okay, so the velocity changes sign only one time, and the velocity goes from positive to negative there. So right here is where the velocity changed signs. I can, since I'm also graphing the x-axis, I can just do second calc 5 for intersection, and then enter, 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 and it'll find me that intersection point. So the time that the velocity changes sign is 2.707. Okay. All right. Part C, find the position of the particle at time 0. So we were given velocity, and we want to find position. So, and we were given this initial position, at time 4, the position was 2. So I'm going to set up a little fundamental theorem. The position at time 4 minus the position at time 0 is equal to the integral from 0 to 4 of x prime, and x prime is also the velocity. So at time 4, the position was 2. And again, x prime is our velocity function, so I will write that in there. I don't have to rewrite what the velocity function is because they used v of t for that, so I can just write v of t. So x of 0, the position at 0, will be 2 minus that integral. And now I'll let my calculator do my work. 2 minus the integral 0 to 4 of my velocity is negative 3.815. Okay. So that would be good if you want to clarify and say the position of the particle at time t equals 0 is negative 3.815. That will work as well. Okay. Part D. Find the total distance the particle travels from time 0 to time 3. So distance from 0 to 3 will be the integral of speed. The integral of speed, and speed is the absolute value of velocity. So since this is calculator active, that's definitely the way I would do this one. Just plug it in your calculator. So math 9, 0 to 3, absolute value, so go get your absolute value of y1 with respect to t, which is x for us in the calculator. These absolute value integrals tend to take a moment to come up. So 5.301 will be the total distance traveled by the particle in that time. Let's take a look at how this one was scored back in 2016. Part A, finding if the particle was slowing down or speeding up, 2 points for the conclusion with a reason, with your reason. In Part B, they gave 1 point for time equals 2.707 and 1 point for your justification. Two points total. Part C, they gave 1 point for the integral. 1 point for that integral. 1 point for uses initial condition. And 1 point for your answer. While I'm thinking about it, one note to make. If you had tried to take this integral here by hand, if you had tried to do it by hand, taking the integral of this requires series to do. Requires our Taylor polynomial, Taylor series to do. So don't even try in this problem to do that one by hand. Okay? Use your calculator. Part D, 1 point for the integral and 1 point for the answer. Okay. Next step. So that was what I would consider that a very straightforward horizontal vertical motion FRQ for the AB exam. Let's take a look at the 2019 exam problem on horizontal and vertical motion. This was from 2019. It was number 2, again with a calculator. And you're going to see this one was a little bit more involved. So they began by, we began with this table and then this information. The velocity of particle P moving along the x-axis is given by the differentiable function. That's an interesting thing to tell us. We probably will need that. V sub P, where V sub P of T is measured in meters per hour, T is measured in hours. Selected values of V sub P of T are shown in the table above. Particle P is at the origin at time 0. Initial condition, they're telling us an initial point. Okay, so the position of P, maybe I'll call it x sub P, at time 0 is 0 at the origin. Okay. All right, part A. Justify why there must be at least one time t from t 0.3 to 2.8 at which v sub p prime of t, the acceleration of particle p, equals 0 meters per hour. Well, the table has v. They're asking me to why a time must exist for v prime, so that tells me I need to use mean value theorem here. Mean value theorem will verify the existence, will confirm that that time has to exist. So here's my thought process. I need to use mean value theorem, so let's give the conditions that mean value theorem applies. For mean value theorem to apply, v must be continuous on the closed interval and differentiable on the open interval. We are given that velocity is differentiable everywhere. Therefore, v must be continuous everywhere as well. So I will say that v sub p is given to be differentiable so V sub p must also be continuous. If you prefer, you can specify the intervals where it must be differentiable and it must be continuous, but by saying this, we're saying that it's differentiable and continuous everywhere, including the intervals that we need. Now let's get to the little equation part of MVT. Okay, we want for the average rate of change of the velocity to be equal to the instant rate of change of the velocity. And specifically, they tell us from time 0.3 to 2.8. So, and they tell us we want that to be 0. So V sub p of 2.8 minus V sub p of 0.3 over 2.8 minus 0.3. From the table, V sub p at 2.8 is 55. V sub p of 0.3 is also 55. That's how we're going to get our 0. So that turns out to be 0, which is what we needed it to be. Therefore, so here's our statement, our MVT statement. I'm going to say, so by MVT, and remember, you don't have to say by MVT, you can just say, so there must exist, whatever. So there must be, you could write this exactly as they write it. Okay, you could say there must be at least one time for time between 0.3 and 2.8, at which, and just write it exactly like they say it. I'm going to use my little symbols by MVT. There exists T in 0.3, in between 0.3 and 2.8, such that V sub p prime at t is equal to 0. And that will take care of that statement with a few little symbols. All right, part B. Use a trapezoidal sum with 3 subintervals. They give me the subintervals to approximate the value of this integral. So I am approximating the value of that integral. Okay, with a trapezoidal sum. Well, remember the trapezoid area has 1/2, and then here we need the difference in the t values, right? So we can go up to the table, or we can go use what they give us here, 0 to 0.3. This is going to be 0.3 minus 0, which you could just write that as 0.3. That'll be the difference in the times, and then we add up the 2 heights there. So this will be 0 plus 55 plus, next trapezoid, the difference in times, and then we add up the 2 heights, 55 plus negative 29. And then the last trapezoid, difference in the t values, and then we're going to add up the 2 heights, negative 29 and 55. And we did not need that time 4 because they wanted us to stop at 2.8. So this is a safe stop spot, so I am going to safe stop there. And come to part C. A second particle, Q, which I kind of knew was coming because they gave me this sub P up here. So a second particle, they call Q, also moves along the x-axis, so that the velocity for time between 0 and 4 is given by this equation, meters per hour. Find the time interval during which the velocity of particle Q is at least 60 meters per hour, and then find the distance traveled by Q during the interval when the velocity of Q is at least 60 miles an hour. All right, so first of all, I have this velocity, and I want to know what's the time interval when that is at least 60. That sounds to me like very simply looking at a graph of that equation. So I'm going to say what I'm doing. V sub Q is at least 60, so maybe it's equal to 60, or maybe it's greater than 60. It's at least 60 on the interval. Okay, now it's just a matter of going and looking at the graph. So I'm going to go to the graph. Better put it in there first and get rid of this. So I'm going to type this in carefully. So 45 square root x cosine 0.063 t squared, x squared. Okay, and then we want to know when it's 60, so I'm going to put 60 here. For my time, do they give me anything on time? 0 to 4. So my x values are 0 to 4. And my y values here, I need to include 60, right? So that negative 3.1 to 3.1 is not going to cut it. I don't know what will cut it, but I need to include 60. I think I'm going to go from like negative 10 to like 100 and see what that does. Don't really need that scale, so I'll just turn that off. Okay, I'm going to see what this does, see if it gives us a nice curve. I think this is going to work fine. Okay, so this is our velocity curve, and the velocity is at least 60 from this time to this time. So I will find those two times. Second calc, 5, enter, 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 will give me my leftmost. So 1.866. And my right. Now before I lose that, if I go and find the second intersection point, I'm going to lose that value, and I'm going to need it in a second when I'm doing the distance traveled. So I'm going to go out and save those, or I'm going to save that x value. So I'm going to quit out of there. I'm going to take that x value and store it in for A. Okay, and I'm going to tell AP what I'm doing. A is equal to 1.866. Okay, and now I'll go back to that graph. Go get that second intersection point. Get a little bit closer over here, and then enter, enter, enter. So the second intersection point is at 3.519. And I'm going to store that in for B. So that x value I'm storing in for B. Okay, and I'll say that B is equal to 3.519. Okay, so I've answered their first question of find the time interval when the velocity is at least 60. Now I'm going to find the distance traveled by Q between those two times. So distance from A to B is going to equal the integral of the speed. Remember, integral of speed. So integral of the absolute value of velocity. So I need integral, math 9, A to B, of the absolute value, grab your absolute value, of what I have stored in for y1, and we get 106.109 or 8. Remember, AP will accept the truncated or the rounded. So I'm going to call that 106.109. I like to round, but AP will also accept the 8 there. Okay? All right. Part D. At time 0, particle Q is at position x equals -90. Using the result from part B and the function v sub q from part C, approximate the distance between particles P and Q at time 2.8. So I'm thinking I need to find the position of P and Q at time 2.8 and then subtract them to get the distance between them. So I think I'll start with finding the position of Q, since I've just done all this with Q. So I'm going to find the position of Q at time 2.8. I know the position of Q at time 0. So I'm going to set up fundamental theorem. So position at Q, I'm going to call it x sub Q. That's position of Q. At time 2.8 minus x sub Q of 0 will be the integral from 0 to 2.8 of x prime sub q, which is v sub q, right? So x sub q of 2.8, x sub q of 0 is -90. I'm going to take that to the other side, so that will be is equal to -90 plus that integral. Time to let my calculator work for me. So I'm going to type in -90 plus the integral 0 to 2.8 of what I have stored in for y1 and this will be the position of Q at time 2.8. And I get 45.938, 45. Since this is not my final answer, I think I'm going to write it like this, because it's not my final answer yet. I don't like to round until my final answer. So that's the position of Q at that time. Now we need to find the position of P at 2.8. So remember up here we were given an initial condition, an initial position for P. So I'm going to set up the same kind of fundamental theorem, except this time with P. So x sub P of 2.8 minus x sub P of 0 will be the integral from 0 to 2.8 of V sub P of T. They gave us that V sub P of 0 is 0, so x sub P of 2.8 will just be that integral. And that integral, up here in part B, they told us to use part B, the integral is approximately equal to this. Okay, now since we need to use this, we could write this all out down here in part D, but I think I'm going to go ahead and find this value. Since I'm going to find the value, I am going to say stop right here, and then I'm going to say what that value is. So back to my calculator, I'm going to add up these numbers. So I have 0.5 times 0.3 times 55, that takes care of that first trapezoid, plus 0.5 times 1.7 minus 0.3 is 1.4 times 55 minus 29 plus 0.5 times 2.8 minus 1.7 times -29 plus 55 And for that I get 40.75, and I really hope that I typed it in all correctly. I know I did because I'm looking at the answer over here on my left hand side, but that's the type of thing that I would probably go ahead and type in twice in my calculator, make sure I get the same answer both times, hope that I don't make the same mistake twice when typing it in, because typing in all those numbers is really easy to make a mistake. So this is approximately equal to, it's approximate because we used that trapezoidal sum, so it's not the actual position, but this position is approximately equal to 40.75. Okay? So now we're going to take this distance and this distance, not distance, position, these two positions, they're not distance, positions, and well, I'm going to make my kind of final answer statement. So the distance between P and Q at time t equals 2.8 is x sub q, so the position of q at 2.8 minus the position of P at 2.8. If you want to put absolute value bars there, you can. It doesn't matter. In this case, it doesn't matter because I know that this is, the position of Q is greater than the position of P. But again, you can always use absolute values there if you want. And that is approximately equal to, go grab this answer, minus that answer. So the distance between the 2 points is approximately equal to 5.188 or 7. You can round this up to an 8 or you can leave it at 7. Let's take a look at how they graded this, how they scored this. For part A, that was the MVT problem, they awarded 1 point for V sub P at 2.8 minus V sub P at 0.3 is equal to 0. That was our numerator of that step. They gave 1 point for that, saying that that was equal to 0. Then they gave 1 point for justification using the mean value theorem. And remember, you do not have to say the words mean value theorem, but you are using mean value theorem when you do this process. They did have a note here. They had a second solution when I looked at how they graded it. They also showed that you could use the extreme value theorem for this problem. I wouldn't. I would stick with mean value theorem, but the extreme value theorem also will work here. So if you want to see how they did that, you can totally just go pull up AB Calculus, or AP Calculus AB FRQ 2019. That's what I do. I Google that, and they will show you all of these scoring guidelines and everything. Okay, part B. For this trapezoidal sum, this was just worth 1 point, and the way they worded this, it says answer using trapezoidal sum. And then in part C, they awarded 1 point for the integral. That was our integral here. And interval. So 1 point for this interval, and then 1 point for the definite integral. That's this. And then 1 point for that total distance we found. And then lastly in part D, they awarded 1 point for the integral from 0 to 2.8 of the velocity of Q. One point for the position of particle Q, and 1 point for the answer. So, oops, 3. a lot of their focus here, therefore, was on particle Q. Okay? All right, that's it. You can try the rest on your own, and let me know when you have any questions.